Go team. First law of thermodynamics. I'm realizing that I'm saying go team at the end and the beginning of every time I pause, so it's just go team, whatever. First law of thermodynamics. The internal energy of an isolated system is constant. Cool. This is the verbal way to write it. Also, the first law is delta U is equal to Q plus W, where delta U, you guessed it, our internal energy. So delta U is U final minus U initial. And so when you change the system, so if you have the system, you want to look at the internal energy that it has from the beginning to the end, you look at the difference between those, that's what your delta U is, okay? So I want to talk about internal energy with respect to what's called a state function. State functions are crucial with thermodynamics because it says that I just care about the initial and the final states. I don't care about the path that it took. Cool, you've heard this path dependent, path independent. Path meaning here's my coffee, it's still cold. If I go downstairs, heat it up, bring it back upstairs, and then let it sit for 2 hours and it's still cold, it still has that same energy. It doesn't matter if I went down and heated it or if it just sits here by itself, it's still going to be cold in that final state. So if I said, okay, what's the temperature or what's the internal energy that it has after sitting for 3 hours or now, it won't matter because it's the same value. And so it doesn't matter if I heat it up, cooled it down, heat it up, cooled it down, heat it up, cooled it down. It's when I define my set point as final or initial, and I look at the difference between those that I care about the delta U. Go team? Here's the problem. Oh, I haven't even gotten there yet. Never mind. Okay, everyone happy with this? Internal energy, delta U. Okay. So, internal energy. Q is heat, W is work. Okay, so if I take all the thermal energy that I have, that's it, and if I take all the work energy I have, you know, blowing and moving, you know, mass migration of molecules and stuff, if I add those two energies together, I've got 10 joules of heat energy, I've got 10 joules of work energy, add them together, I should have 20 joules of internal energy. Go team? Okay. So this is a heat energy, this is a work energy. Both of these depend on the path. The work energy I put into fanning molecules towards you right now, it's going to depend on how long I fan them and how long you take in time. How are we measuring that work energy that's going into the system? Likewise, if I put this on a candle, if I leave it for 10 minutes, if I leave it for 20 minutes, if it depends how much heat energy I put in, it's path dependent. So how then does this work? We've got path dependent, not state function, equal to state function. I hope this pisses you off. Because it should. It shouldn't make sense. But it will. I mean, this is the first law of thermodynamics, but that's one of the beauties behind it. You have two things, heat and work, that are path dependent. We can't work with those. We can't work with work. It's really hard to quantify what equation dictates heat, what equation dictates work, without making some assumptions. And one of the biggest, it's not even an assumption, it is a law, is that if you add the heat and the work together of a system that has undergone a change, you will get a state function result. I'll say that one more time. If you add the heat energy and the work energy of a system that undergoes a change, you will get, there exists a function such that delta U is equal to Q plus W is true. Glorious. Okay. So that's what we're going to start working with. We know heat's going in, we know work's going in, but we can't work with those very well. So through the first law of thermodynamics, for an isolated system, we know that the internal energy is constant. No work going in or out, no heat going in or out. Therefore, Q and W must be the same, or not the same, but must be constant. Therefore, if it's an isolated system, delta U should be constant, which means delta U is not changing. It's kind of cool. Okay, pause. Okay, let's dive deeper into the internal energy. So we know that delta U is equal to Q plus W. And so I want to look at the molar. Again, little sub m means molar, so per mole. U is dependent on temperature. We know this because from the first law, we know that heat and work are related to internal energy, and heat contains thermal energy. Okay, or heat represents thermal energy. So there's going to be some fundamental at 0 Kelvin energy associated with the fact that the matter itself exists. Then we have plus 1/2 RT per degree of freedom. Okay. Now, internal energy is energy internal to the system, and RT represents thermal energy. And so R, you've got 8.314 joules per mole Kelvin. Multiply that by whatever Kelvin you have. Cancel, cancel. This is joules per mole. And so that's the joules associated with that particular temperature. So this is one of the reasons that I don't like people saying that temperature and heat are the same thing, because they are not. RT is thermal energy. T is temperature. Keep them separate. Or actually, who cares about temperature? Doesn't mean anything. It just means that heat's going to flow. And so you really need to always multiply temperature by R just to give you the thermal energy, so you can talk about the actual flow of energy, the quantity of the flow of the heat. What's funny, the caloric theory was that there were these little heat corpuscles that would transfer, and those were called calories, and the name stuck. So the metric system is joules, but then the imperial system, whatever, is calories, which of course the United States follows annoyingly. Okay, per degree of freedom, you have 1/2 RT for, well, we'll get to that in a second. What is a degree of freedom? Best by example. So for a monatomic gas, say helium, you only really have a translational degree of freedom. Helium just moves. It doesn't vibrate, it doesn't rotate, it doesn't store energy anywhere but its translational motion. So U of M as a function of temperature for helium would be UM at 0, so whatever that value would be for 0 Kelvin, plus 3/2 RT, because it has both an X, a Y, and a Z direction. So 1/2 RT for the X, 1/2 RT for the Y, and 1/2 RT for the Z directions. Combine those together, 1/2 plus 1/2 plus 1/2 gives you 3/2 RT for monatomic, okay? If I had linear, say a diatomic, so let's say N2, I have translation, but I also have vibration. And I also have rotation. Well, that's pretty cool. So I have my fundamental 0 value, whatever that number might be, plus 1/2. Actually, I'm just going to go ahead and say 3/2 RT for my translational. And then I'm going to have plus 1/2 RT for my vibrational, plus 1/2 RT for my rotational. Go team. And so, but if you look at this, I have the rotation of, so 1/2 RT for the vibrational, but then also for rotational, I will have in the X direction, but then I will also have, so it's going this way, but then I will also have it going around. So you've got one going around this axis, and then you've got the other one going around that axis. So there's going to be 2 rotational degrees of freedom. So I'm going to say plus 1/2 RT for rotational. Okay. And so when you add 3/2 plus 1/2 plus 1/2, well, actually, let's assume no vibrations. That's what I want to do. There we go. Assume no vibrations. I'm too lazy to edit that out. Anyway, assuming vibrations are very challenging, and we'll get to those in a couple weeks. So translational and rotational. So this is a linear, basically a dumbbell. And so you've got energy in the degree of freedom, energy in the degree of freedom, and energy in the degree of freedom in terms of 1/2 RT. And so this gives you, this whole thing would then be 5/2 RT for a linear molecule. If you had a nonlinear molecule, let's say water, it would have an additional, so you're not counting the, if the, this is not a rotation, this is, and this is. So this one's not. If, however, it was like this, it'd be this way, and that way. So that would work. So for a nonlinear molecule, you'd have UMT is equal to UM0 plus 1/2, or so 3/2 RT translational plus 3 rotationals, and that would give you 3 RT. Okay? So depending on your system, you're going to have a different function for each of your internal energies. Yee, what do you do with that? I will gladly tell you. Okay, I'm going to pause and clean this up a bit. Much simpler. I've taken delta U and I have subtracted it from delta UM at T. So UMT minus UM0, that's technically just a delta U because I'm looking at the difference between the two at the 2 different temperatures. So for a monatomic gas, 3/2 RT, 3 degrees of freedom, 1/2 RT for each. For a linear molecule, 5/2 RT. For a nonlinear molecule, 3 RT. Cool. The important thing to note is as T goes up, delta U goes up. If T is isothermal, if T does not change, that's gold right there. You're gonna, there's some, as soon as it's isothermal, you're like, oh, delta U 0, yes. It makes things easier. Okay, so it's good to know this is the relationship. Delta U is the energy internal to the system. Go team. Okay, oh, last but not least, there's a sign convention. So back to first law real quick. So let's say that we've got, so here's an example. It takes 100 joules to compress a spring and 15 joules are lost as heat. What is the internal energy? So delta U of the spring equals Q plus W. It takes 100 joules to compress a spring, okay? So if it takes it in, it's gained. So we have Q plus W, and so that means plus 100 joules because it's gained. And then we've got 15 joules are lost, minus 15 joules. Cool? So that means we've got 85 joules, the change in the internal energy of the spring. This is lost. So if energy's lost, oh, by the way, anytime you set up an equation, it's always good to never just write numbers on the board or on their paper. Always write out your equation first. Even if your equation's way up here, it's proper procedure to write immediately above and then the numbers go in immediately below. So notice how I rewrote it. You might just feel compelled just to write this on the board. Technically, that's incorrect and harder to follow because the way that the I reads mathematically, the equation, and then the numbers in input into the equation. That's not just me being picky. That's how we theorists do it. Okay, so sign convention. I want you to think of a bank. Here's the bank. Okay, if money goes into your bank account, your balance goes up. If money comes out of your bank account, everyone's sad face. Money, or the number goes down. The bank account number goes down, negative. Okay, hopefully not negative, but money goes in, energy goes in, positive value. Energy comes out, negative value of your system. That's why it's very important to define your system. You are not the system. The bank is the system in this analogy. If you want to make yourself the system, you lose money, negative. You gain money, positive. Then you are the system. Because if you're the system in this case and the bank is, or if you're the surroundings in this case and the bank is the system, if money goes into the bank, you're losing it. See the exchange there? So you lose the money, but the bank gains the money. So they get positive, you get negative. All right, go team. I think that's all I want to talk about with delta U for now.